Hello, my name is Elsa Mendoza. I'm from the University of Nottingham, and I am explaining my research on exploring resilient, adaptable, and feasible approaches to retrofitting listed commercial buildings with a case study on Douglas Primary School in Nottingham. Why to retrofit? The emissions from the built environment represent a high amount of the carbon emissions, and they need to be reduced by 50% by 2030 to be able to meet the net zero targets for 2050. The housing stock is responsible for 69% of these emissions, and the commercial buildings are responsible of 6%. So the standards that are being developed are more focused on housing now. So there's a gap of what can we use to assess commercial and public buildings. Around 80% of the building stock that will be here in 2050, it's already built. And from this stock, England has over 400,000 buildings listed, so protected and with restrictions to make modifications. The methodology I used was divided in four steps. First, the understanding of the approaches, the standards and guidelines available, the case study analysis, then a post-occupancy evaluation to know how the building is performing today and what is the baseline to improve, and then an operational carbon analysis to prove some iterations that could be done to benefit in the carbon emissions. The case study is a former primary school in Nottingham built in 1885. So it's a Victorian building with a grade 2 listed characteristics with an area of 1,343 meters squares. It has a solid wall with red brick facades, terracotta dressings, hipped roof, and it has shaped gables and round-headed sash windows that are some of the features that need to be protected with any design intervention. So the first stage of comparing the approaches included some housing standards and guidelines that are now available as LETI, EnerFit from Passive House Standards, AECB, and also a reference from the Old House Eco Handbook that provides technical strategies for old buildings. These were compared for different cases: a typical average semi-detached house, a Setland house that is a retrofit precedent study, and the Foundry office that is also a retrofit project of an office in London, and then the primary baseline that it's the building assessed. The case 3, that is the Setland houses following EnerFit standards from Passive House, achieved the highest energy reduction. And the baseline building has 10 times higher energy demand for heating. So the post-occupancy evaluation, I did some data gathering on temperature, daylight, and sound, and it shows that there's a one-day difference from the data from the outside temperatures with the inside that proves the thermal mass storage capacity of the building. The baseline show that all the rooms were mostly cold and a little overheating risk on one of the rooms that was south-oriented, with a high heating demand of 512 for the building, that it's far away from the 60 target from LETI. So a series of interventions were performed, additive, so each one was based on the previous one. And the roof intervention by insulating a warm roof was the most beneficial, with a 93% improvement. And the MBHR system proved a negative 6% that would need to be further assessed. And the final heat demand was of 82, that is still over the targets. So this was assessed also by a dynamic simulation that with the insulated building, we have now more overheating risk, but the comfort range between 20 and 25 was highly improved but still we have a lot of heating demand there. It was also tested for different weather scenarios. For 2020, that it's the currently, 2050, that it's the net zero target, and beyond to 2080. Natural ventilation was proved to resolve the overheating in this case by reducing it in all the rooms. So the conclusions are that the whole life carbon of operational energy was reduced 83%, but it's still not enough to get to the net zero target because all the limitations that the listed building had. So the standards need to be tailored for commercial buildings that would need to also take into account the limitations for this typologies and the age of the buildings to get a better performance. Thank you.
Thank you very much. Questions?
Out of curiosity, you said that is a school, right? But then when you introduce, you say that is a mixed-use commercial building. Was it a specific reason that you chose that typology in terms of benchmarks or maybe data that you could access rather than educational buildings?
Yeah, it was a former school, and the use was changed. So one of the potentials identified of reusing and retrofitting is that it could be adaptable and reused for new demands for occupancy. And it's actually an artist organization with multi-purpose activities that include bakery, artist galleries, art studios. So it's a mixed use now.
Okay.
Hello, and thank you for the presentation. I have a question about the passive natural ventilation. Once you're doing the simulation, does the simulation or does the process take into account only the window or the wind speed as well? And also, like, this goes back to the discussion we had with the previous batch. With the overheating last week here, outside was relatively cool. But then with the windows, you don't have enough wind speed to remove the heat. So is this taken into account within the software or within what you're proposing? Thank you.
Thank you for the question. This was just taking into account 50% of the openings for all the windows, because currently the building has not operable all the windows because of the difficulties of the age of the building. So improving the windows and replacing them would allow to have a 100% openings availability. So it was only that value taken into account, not the speed, but it showed a really good performance from the basis without ventilation and with opening 50% of the sash windows.
Can we leave the question for the discussion, please? Good, great. Thank you very much, Elsa.